In chapter 3, we will be looking at conformers or conformational isomers. So, in this lecture, we will be covering the following: a review essentially of dash wedge representations of molecules. So we'll review that. We'll also review the Newman representations of molecules. They're such an important representation of the three-dimensional aspects of molecules that they are frequently used in organic chemistry. Next, we'll look at the conformers and the relative energies of different conformers. Okay, so we'll have to define conformers and then we'll look at the relative energies. But of course, we'll use the Newman representations for these different conformers to show the relative energies. We'll look at the actual value or relative values of some of these conformers. Then we'll look at conformations with low energy barriers. Literally can separate these depending on the energy barrier. And lastly, we'll look at cyclic compounds or conformations of molecules that are cyclic. Before we do that, however, let's do a quick review of what we did last lecture. So last lecture we introduced symmetry elements, and remember these are elements that are very useful in determining if a molecule is symmetric or not. This is important because symmetric molecules are typically not optically active, as we have seen here in the meso compound. So you may want to review that. So the meso compound has chiral carbons, but it has a plane of symmetry and its mirror image is the same as the original. Then last lecture we looked at applying the symmetry elements to amines. Notice that amines, they do not have 4 different groups bonded to the nitrogen, but if there are 3, including the pair of electrons, it can be optically active because especially if the groups are pretty large that's bonded to the nitrogen. Then we looked at allenes, which are double bonds that are in consecutive order. Then we looked at adamantane, which is a rigid bicyclic compound, and we looked at spiral compounds and using the symmetry elements. Next we look at a trope isomer. An atrope isomer is one that results based on the restricted rotation about a carbon-carbon bond or about a bond. Lastly, we looked at the properties and separation of asymmetric compounds. Okay, remember that chiral compounds or enantiomers, they differ primarily, essentially actually, by one property, and that is the direction in which it rotates the plane of polarized light. Then lastly, we looked at stereotopicity, which deals with the hydrogens that are in different environment in molecules, even though they look as if they're in equivalent environment, but typically they are in different environments. And one way we can tell is that if we substitute one of the hydrogens, we can get enantiomer or diastereomer. And don't forget, if you have diastereomers, the diastereotopic hydrogens, the NMR can detect that difference. Okay, so let's look at today's lecture. So first, let's do a review of the dashed wedge representation here. So we're looking at the dashed wedge. So let's review that. So here is a methyl, a carbon, and an ethyl group. These are all in the plane of the paper or the computer screen. The wedge is in front and the dash is in the back. So this is a way of trying to represent the three-dimensional arrangement of the atoms around carbon. So here's another one, another carbon right here. It has this CH2, CH3, which is in the plane of these four carbons here, and this one is behind because it is a dash, and the wedge is in front. So that's the dash wedge representation of molecules. Let's look at the Newman projection. You may recall that the Newman projection is basically looking at the molecule down a carbon-carbon bond. So if you look at the dash wedge here and look down this bond right here as shown here, what you'll see is this carbon, which is in front, and you won't be able to see the back carbon because it is directly behind this carbon. So what's shown here is the methyl, the hydrogen, and the ethyl, which are on this front carbon, and here they are. And on the back carbon, which you cannot see, it has a methyl, a hydrogen, and an ethyl. And here's the methyl, the hydrogen, and the ethyl on the back carbon. So this is the Newman projection by looking directly down a carbon-carbon bond. So what you should be able to do is to convert here the dashed wedge into the Newman, or manipulate these two representations. So here again is the front carbon and the back carbon. A slight rotation out the plane of the paper will put this in front, and you can look down to see the back carbon, which we represent here with a big circle. And of course it has the groups that are bonded to it. We have some names for this. So this is the eclipsed conformer. As you can see here, we have the methyl group bonded to a carbon, to another carbon, and here's the ethyl group. So these are right behind each other. As we can see here, they're right behind each other. So as these groups are behind each other and these groups are behind each other, notice again, these are on the same side and these are on the same side. So that's represented here. So this is the eclipsed conformer, where this is the dashed wedge and this is the Newman of the same eclipsed conformer. So let us look at the three important representations that are used in organic chemistry: the fissure, the dashed wedge, and the Newman. So here's the fissure, just to refresh your memory. Here's a horizontal line right here. So this group here and this group is in the horizontal plane, so it's sticking in front. And of course these groups here are in the back. So if you build this molecule, you'll see that it's really an eclipsed conformer, where these four groups here are in front, and this group here and that group here is in the back. Here is the dash wedge for the eclipse conformer. So notice again that this methyl and this methyl are right across from each other, and here are the groups that have groups in front and behind. Here's a Newman. So now we're looking right down these carbon here, and now we have the bromine, methyl, and hydrogen right here, and on the back carbon we have the chlorine, methyl, and hydrogen. Notice how it's drawn down as eclipsed. So we put this line here as close as possible to this group here. So these two groups here are directly behind each other, so we put them as close as possible. Same here and same here. So that's the eclipsed Newman conformation. All right, let us look at conformational isomers. You may recall last lecture that isomers are really different from each other. So we have stereoisomers and we have structural isomers or constitutional isomers. What we'll be looking at, or what we have been looking at for the past week, is basically stereoisomers, where the basic bond-to-bond connections are the same. However, the orientations in space are different, hence stereoisomers. So let's look at this molecule here. So we have a methyl, a carbon, and an ethyl group. So what we have here is a staggered conformation, or the anti-conformation. If we should rotate around this bond here by 180 degrees, as you can imagine, this will come up as shown here. So we'll get the eclipsed conformer. So these are conformational isomers that are derived by the rotation about a carbon-carbon single bond. So that's by definition what conformational isomers are, and these are different from enantiomers and diastereomers that we saw last lecture. Let's look at another representation and using the Newman projection here. So we're using the Newman projection here. This of course is the staggered, or the anti, where we have the methyl and the ethyl. On the front carbon here we have the methyl, and on the back carbon we have the ethyl and these groups here. Rotation around this carbon here, the front carbon and the back carbon, by 180 degrees would bring this group all the way over to here, as you can imagine. So here it is. So that becomes the eclipsed conformer. So these are conformational isomers. So we're taking the staggered conformer, and by rotation of 180 degrees about the carbon-carbon single bond, we now have another conformer which we call the eclipsed conformer. Okay, so let's look here at some of the names that we'll use. So here's a molecule, 3,4-dimethylhexane. So if we rotate about carbons 3 and 4, notice rotation is possible about any carbon-carbon single bond. But here we're looking at carbons 3 and 4. So rotation here, one possible isomer is called the anti-conformer, which is really staggered, but the anti means the two largest groups are furthest from each other. Here's the eclipsed conformer, where the groups are directly behind each other, right across from each other. Here's a name that you may recall from your organic, the gauche conformer. This by definition is the staggered conformer, where the two largest groups are close to each other in the staggered conformer. So here are the two largest groups, the ethyl group and the ethyl group. This is on the front carbon, this is on the back carbon, but they're right across from each other in a staggered conformation, and hence that name is the gauche conformer. All right, let's look now at the energies, the relative energies. Are there any difference in energies between these conformers? So let's look at this molecule here, 1,2-dibromoethane. So here's the bromine, which is pretty large, as you can see from your periodic table, and here's bromine that's pretty large. These two bromines are on two different carbons. And notice that this bromine here and this bromine here are they are opposite to each other. Rotation around this bond here, so here's this carbon-carbon single bond, and rotation here by 180 degrees will give us this one in the dashed wedge. So in other words, this will come up to here, as you can see here. Now let's see if we can analyze to see the energy difference. Large groups tend to want to be as far as possible from each other. So here's the bromine, pretty large. Here's another bromine, pretty large. So it goes in the anti-conformation, more stable based on that definition. If we should do a rotation by 180 degrees, it brings these two bromines right across from each other or close to each other, and this is the less stable conformer. This is the less stable conformer. As you can see here, the energy difference here is about 3 to 5 kcals per mole. So in other words, this is about 3 to 5 kcals per mole more stable than this conformer, which is also called the eclipse conformer. Now let's see another way of looking at this, and this is described nicely in the textbook by looking at the dihedral angles. So remember, the dihedral angles here is the angle that you get by looking down a carbon-carbon single bond and the angle that's generated between any two groups. So here is the carbon-carbon single bond. We're looking down. There's a bromine on the front carbon and there's a bromine on the back carbon. So the dihedral angle between this bromine and that bromine looking down the CH2 is 180 degrees. So that's another way that is described, is the anticonformer has a dihedral angle of 180 degrees. Let's look at this one. If you rotate by 180 degrees, let's see what's the dihedral angle between the bromine, the carbon in the back, and the other bromine. This is 0, as you can see here, because they are directly behind each other. So the bromine, CH2 in the back, and the bromine in the back, the dihedral angle here is 0. You should be able to look at the dashed wedge and determine what's the dihedral angles also. Here's the bromine, CH2, and the bromine. So the dihedral angle between this bromine and this bromine here is 180 degrees, much easier to see using the Newman projection. So hopefully you can see why sometimes we use the Newman projection and sometimes we use the dashed wedge projection. Here's the other example. So here's a bromine, a carbon, CH2, and a bromine right across from each other. So looking down here, what you'll see is a bromine, a CH2, and a bromine, and the dihedral angle here is 0. So again, you should be able to understand what's the meaning of a dihedral angle and use that in describing the relationship between two atoms in different conformations. Okay, let's look at the relative energies. As we said, two bromines or two groups being close together is high in energy. As you can see from this energy profile diagram here, here's energy in this direction. So what's in the high region here is high in energy. What's down in this region is pretty stable or relatively stable. So let's rotate around this bond. So first of all, here is the bromine sitting right across from the bromine. So that's high in energy because that's the eclipsed, with a dihedral angle between these two bromines here of 0 degrees. High in energy, so that's why it's way up here in energy. A rotation here by 60 degrees puts this, well actually right here, puts the bromine right here, and as you can see that interaction is minimized, so lower in energy, gives you a staggered conformation. If you rotate this further by another 60, we have here another eclipse. So this hydrogen and this bromine here are sitting right behind each other. Notice because bromine here is large and hydrogen is smaller than bromine, it's not as high in energy as this one, but still relatively high in energy here in the eclipsed conformer. Rotate by another 60 degrees. Here we have now this staggered, where the bromines are furthest from each other. So in other words, this is the most stable, the anti-conformer, the staggered conformer. And we can rotate some more, we get another eclipse going back up in energy, etc., etc. Here's the gauche conformer, and we can go back to here, which is back to this conformer. So again, what you should get from this is the relative energies of different conformers. And remember, conformers here results from the rotation about a carbon-carbon single bond. Okay, let's look here at conformational isomers, where there is a little more difficulty in the rotation. So let's look at this conjugated system here. You would expect rotation to occur right here. Relatively easy because that's a single bond. But if you draw the resonance structure here, you can see that it has some double bond characteristics. So that's a little more difficult to separate. Or the equilibrium or the energy of activation between these two isomers here which would be a little higher than that of your typical carbon-carbon single bond. Notice, however, though, because rotation can occur here, we get two isomers. This is the trans and this is the cis isomer. So notice the E and the Z that we did in the last lecture, or was mentioned in the last lecture. Here the Z means that here we have a hydrogen and a hydrogen here. So if you look at the priorities around these groups here, you can see that they are in the Z conformation. The two groups on the same side here and here. So these two hydrogens are on the same side here. So that's why we have the Z isomer. And this is the E isomer. Look at this reaction here. This is a pretty stable molecule, benzene ring with a double bond here. In the presence of light, however, we have a pericyclic type reaction, which we'll look at. You've seen in your undergraduate organics. So it opens up. And of course, now we can have rotation here. But of course, we will now have a double bond here, but it's possible to have a single bond characteristic. So therefore, it's possible for rotation to occur here. And we can do the same thing here. We can draw resonance as we did before. And you can see that this is some single bond characteristics here. So it's possible to rotate from the trans to the cis, and of course the trans is more stable. That's why the equilibrium here favors the trans isomer. Let's look at this one. Notice here that there's a carbon nitrogen bond, single bond as drawn. But of course, as you know, it has some double bond characteristics because the unshared pair of electrons here can be delocalized onto that oxygen, giving some double bond characteristics here, which makes it a little difficult to rotate. In addition, for this molecule, there are groups here that tend to restrict the rotation, large groups. So the activation energy separating these two pretty high. So that's why it's possible to separate this isomer in terms of the conformational isomer and this isomer, conformational isomer, because of that energy gap between these two isomers. This has a melting point of 64 to 65, and this one is much higher, 105 to 106, all because of possible rotation here restricted based on the large groups, and also because of the double bond characteristics of the carbon nitrogen bond right here. You may be wondering, how can we make such observations? Typically done by X-ray or NMR, different environments, or molecular modeling can give you some good estimates of the energy difference between these. As we'll see later on, if you should get any one of these isomers, conformational isomer, and supply enough heat to it, you can get them to convert. But as you lower the temperature, you can isolate them here. Here's another example here. So we have a double bond characteristic here, and notice that it looks as if there was rotation here against the double bond. Of course, you learn from organic that the double bond is rigid. There's no rotation about a carbon double bond. It's a pi bond and a sigma bond. But here we're showing rotation where this group here comes back over here. So as you can see here, we can draw resonance structure here to give some single bond characteristic here to that carbon double bond, making rotation easier than if we did not have that resonance structure. So again, look out for the possibility of bond rotation for a carbon double bond based on resonance or conjugation. Here's another example. Here's a double bond, but it looks as if there's rotation here. This group is down here and it's up top. As you can see here, we can draw resonance, and this is unique because here we have two aromatic rings. So here is the aromatic ring here, 2, 4, 6 electrons. You will recall that if you have 6 electrons, it meets the Huckel rule for aromaticity. So this is aromatic. Here we have 2 electrons in a ring, so that also meets Huckel requirement for aromaticity. So we have 2 aromatic rings. So as you can imagine now, rotation around this bond is fairly easy because of the resonance structures generating 2 stable ring systems here. Here's another example. I think we did this last lecture, which is a trope isomer. Here we have rotation here, and so we can bring this one over here and this one over here, and of course at very low temperature we can see these as 2 isomers. You can see these as 2 isomers. That was just a review based on what we did last lecture. Okay, let's look here now at cycloalkanes. Is it possible to have conformers for cycloalkanes? Let's look at the smallest possible cycloalkane, cyclopropane. As you can imagine here, there's very restricted or limited internal rotation between a carbon single bond because it's very rigid. So there's literally no rotation here. Angle strain is extremely high. So what happens here, we have trans and cis possibilities where the groups can be above or below the plane of that cyclopropane as shown here. Here's just another representation using your dashed and wedge representation here. Let's take it further. So let's look at the cyclobutane. As you can imagine, now we have a bigger ring system compared to the cyclopropane, so we still have limited internal rotation as shown here. So we have less angle strain compared to the cyclopropane, but still it's rigid. But we describe this ring here as puckered here. right? So what we have here is we can still do the cis and trans. So we have a group here and here. You can see that's above and below this puckered ring system here. So that's the trans. And if you should switch this group for this group, so we have here, so this would be the cis arrangement, essentially on the same side of the puckered arrangement. So once again, this is due to very limited internal rotation. It's not as flat as the cyclopropane, but it's a bit puckered. Let's see what happens here with the cyclopentane. As you can imagine, less angle strain, more flexibility between these carbon-carbon single bonds here, and in fact they can in fact rotate a little bit, but not much, to the point that these hydrogens are showing now as different. So we can describe these as HA axial and HAE equatorial. What does that mean? That means that this plane here for the cyclopentane ring, the equatorial hydrogens will be sitting in the same plane as here. If you have a model set and build it, you can see it. Of course, without breaking it because of the strain. There's a little strain there. And the hydrogens that are above and below are described as axial. So a little more flexibility causes the hydrogens to now differentiate itself that are bonded to the carbons as axial and equatorial. So what we have here is, if we should put two groups on, such as the methyl group and the methyl group, notice it's on two sides here of the cyclopentane ring, and they are axial and axial, so that would be trans because they are on opposite sides of that cyclopentane ring. Here this would be equatorial and axial, so this would be cis, dimethyl cyclopentane. Let's look at this cyclohexane, which is a very common ring structure in organic chemistry and a very common ring structure that is found in nature. Here we have a lot more flexibility between the carbon-carbon bonds, less angle strain compared to the cyclopropane, definitely, and the cyclobutane, and of course the cyclopentane. What you'll discover is if you build this, it's very flexible. Very flexible. You can literally take this carbon here and pull it all the way up, and you get a different conformer based on slight rotation of these carbon-carbon bonds. Because there are two conformers possible, this one is called the chair conformer, essentially because it looks like a chair. Here's the head and here's the feet. And the other one is the boat conformer, because it looks like a boat, so here's the boat, sit right in here, so we have the boat conformer. The question now becomes, which is more stable? As you can see here, there's interaction here between this hydrogen and this hydrogen. So because they're close to each other, and as we mentioned earlier, groups that are on molecules, they want to be as far apart as possible. So therefore, this conformer, the boat conformer, is described as less stable conformer, or the less stable conformer compared to the chair conformer, which is the more stable conformer. So from here on, the conformer that we look at or examine for the cyclohexane ring will be the most stable conformer, which will be the chair. So let's look at what happens here. As I mentioned, if you take this carbon and literally pull it up to here, you get a boat. And then if you take this carb and pull it back down to here, you get the other chair. So there's a constant equilibrium. that's happening here. At room temperature, it's constantly going from one conformer to the other. So here we have the chair. We call this the half chair or the boat. As you can see, here's the boat, and it flips back down to the chair. So we have the chair conformer. These are the most stable conformer, the chair, but at room temperature, because the energy of activation for these to happen is pretty low. So there's enough energy at room temperature for these ring flip, we call them ring flips, to go from the chair to the boat to the chair. Of course, the majority, the equilibrium favors the chair conformer. All right, let's look at the chair conformer. Since we have decided that is the most stable conformer, so let's carry out our analysis based on the chair conformer. Again, here's the chair conformer here, and each carbon has, of course, two hydrogens. We can describe these as the equatorial and the axial, just as we did for the cyclopentane. So here we have the axial above the plane and the equatorial within the plane of the cyclohexane chair conformer. So this is the most stable, and these are the descriptions of the hydrogens that are bonded to each carbon. Notice each carbon has an axial and an equatorial. Same here, equatorial, axial. Here, axial, equatorial. A little tricky to draw, so you may want to practice drawing the chair conformer with and indicate the axial and equatorial hydrogens. Let's look at a substituent on the chair conformer of cyclohexane. So here's a carbon. So here's a substituent here, the methyl. So as we say, we can take this up here and take this back down here as indicated from one chair through the boat to the other chair. Notice what happens. This is now in the equatorial position, and now it switches to the axial position by flipping. The question now becomes, out of methyl cyclohexane, which is what this is the conformer that has the methyl group in the equatorial position more stable or less stable than the conformer that has the methyl group in the axial position? Pardon me. So let's do that again just to make sure. If you do a ring flip where this is in the equatorial and you flip the ring, it will go in the axial position. The question is, where will this equilibrium here lie? To the left or to the right? Let's look at this one. You can see that this methyl group here in the axial position is close to the axial hydrogens on the three carbons over here. So that's why that's called a 1,3 diaxial interaction. It's like we have a typo here. So we have a 1,3 diaxial interaction here. That makes it less stable. In the equatorial position, there's more space and no interactions here with the equatorial hydrogens because there's more space. Hence, groups that are in the equatorial position of the cyclohexane is more stable than groups that are in the axial position of the cyclohexane ring, primarily due to the interaction here, the 1,3 diaxial interaction. Okay, let's look at disubstituted. So here's a carbon with a methyl, and here's a carbon with another methyl, and here we have a 1,4, 1, 2, 3, and 4. So it's a 1,4 dimethyl cyclohexane. We can again do what we did before, the ring flip. This comes down, this comes up. If we do that, the equatorial is now converted to the axial, and this equatorial is now converted to the axial. As you can imagine, this is now far less stable because this methyl group is interacting with these, and we have this methyl group here interacting with these hydrogens, the 1,3 diaxial interaction as we saw on the previous slide. So this conformer is less stable than this conformer, which is more stable, in which the groups are in the equatorial position. We can describe this as the trans, or the EE14-dimethyl cyclohexane. Doing the ring flip will only create another conformer, and this will be the trans, same trans, but now we have the AA axial 1,4-dimethyl cyclohexane. So again, you should be very familiar with the relationships between groups that are bonded to the cyclohexane ring in terms of the equatorial versus the axial and their relationship. Let's look at this one. So here we have the equatorial methyl on the first carbon, and we have on the fourth carbon here a methyl that's axial. So you can see if you do a ring flip here, this brings it to the equatorial. Ring flip here, this brings it to the axial. So we still have an equatorial and an axial, as we have here an equatorial and an axial. So they're about the same stability. But the take-home lesson here is the relationship is a cis. So this is an axial equatorial, and likewise this is an axial equatorial 1,4 disubstituted, or a 1,4 dimethyl cyclohexane. So you can see here we have different isomers, but within these isomers we have conformers based on the internal rotation here, or ring flips. So I think this is a summary of what we've done so far. So for the cyclohexane rings, we can have the cis and the trans arrangements. Two groups bonded to the cyclohexane. As you know, they can be 1,2 relationship, 1,3, or a 1,4. If it's a cis, it's an AEEA, equatorial axial. So this will be very helpful. We won't go through all of them because this is a review again from your organic. But again, you should know what's the relationship between a 1,4 if the groups are in the axial, that would make it a trans, or if they're in the equatorial, that makes the trans, and that makes it very stable. I think this is the end of this chapter here for conformational analysis of isomers. So remember again, conformational analysis here is basically isomers or stereoisomers that come about primarily because of the rotation, or should I say essentially because of possible rotations around carbon-carbon bonds. Okay, so this is it for chapter 3. We won't go into the computational aspect just yet. So the next lecture we'll go into is the intermediates that are possible for organic chemistry reactions. So we are on track with the syllabus, so keep reading the material in your textbook and keep following the syllabus, and I'll post that lecture next week.